June 30th, 1944, Saipan, Mariana Islands, 2:47 in the morning. Lieutenant Dale Haberman sits in the cockpit of his P-61 Black Widow, staring at a green glow that shouldn't exist. The SCR-720 radar scope, mounted on a panel to his right, shows a single bright pip against the circular display, a target, 15 miles away, moving at 200 miles per hour, completely invisible to the naked eye. Outside the canopy, absolute darkness, no moon, cloud cover at 8,000 feet, the kind of Pacific night where a man can't see his hand in front of his face, where the horizon disappears into blackness so complete that pilots lose all sense of up and down. Target bearing 090, range closing to 13 miles, says Lieutenant Raymond Mooney from the radar operator's seat in the fuselage behind Haberman. His voice crackles through the intercom. Single contact, looks like a Betty. Haberman banks the massive twin-engine fighter toward the intercept bearing. The P-61 weighs 32,000 pounds fully loaded, as much as a medium bomber. Twin Pratt & Whitney R2800 double Wasp engines, each producing 2,000 horsepower, pull the aircraft through the turn. 66-foot wingspan, 4 20mm Hispano cannons mounted in the belly, 4 .50 caliber machine guns in the dorsal turret. And in the nose, behind a fiberglass radome and visible to enemy radar, 412 pounds of electronics that can see through total darkness. The pip grows brighter as range closes, 12 miles, 10, 8. The Japanese pilot has no idea death is tracking him from beyond visual range. Germany's Wurzburg radar fills entire rooms and weighs tons, static installations that defend fixed positions. Japan has nothing comparable to American airborne radar, but this single American fighter carries a complete search and tracking system that operates while the aircraft maneuvers at 360 miles per hour. At 6 miles, Haberman sees nothing ahead except darkness. At 4 miles, still nothing. At 2 miles, Mooney spots the silhouette visually, a Mitsubishi G4M Betty bomber, barely visible against distant clouds lit by starlight filtering through breaks in the overcast. A single-engine fighter tucks in close beside it, escort protection that won't matter. "Start your run," Mooney says. Haberman throttles back, matching the Betty's speed. The Japanese bomber climbs to 17,000 feet, trying to reach safety in the clouds. The P-61 follows. The radar doesn't lose contact. Doesn't care about clouds or darkness or evasive maneuvers. At 1,000 feet behind the target, Haberman opens fire. 4 20mm cannons erupt simultaneously. Tracers walk across the Betty's fuselage from tail to cockpit in 2 seconds. The bomber's fuel tanks ignite. The explosion lights the ocean below, a fireball that burns for 3 full seconds before the wreckage plunges into the Pacific. The first P-61 aerial victory in the Pacific theater. The Japanese escort fighter breaks hard left, desperately trying to maneuver behind the American aircraft. Haberman rolls, dives, uses the radar to track his attacker through the clouds where no human eye can follow. The Japanese pilot is good. He survived this long by being good, but he's fighting an enemy he can't understand. Every turn he makes, the P-61 follows. Every evasive maneuver, the radar tracks him through. After 2 minutes of maneuvering, the Japanese fighter flees at full throttle, disappearing into clouds at wave-top altitude. He never gets a single firing solution. How do the Americans see in total darkness? Japanese pilots would ask this question for the next 14 months. Some suspected radar. Most didn't believe it was possible to miniaturize radar enough to fit in a fighter aircraft. A few thought American pilots had somehow developed cat-like night vision through diet or training. But the real explanation was far more impactful, proof that changed everything about how this war would be fought. If you want to see how this industrial marvel rewrote the rules of engagement, support us with a like. It helps us uncover more buried stories like this. Subscribe if you haven't already. The truth was simpler and more devastating. American factories had taken a British invention and turned it into a weapon system produced by the thousands, each unit small enough for a single aircraft, precise enough to guide automatic gunfire, manufactured on assembly lines by companies that had been making telephones and automobiles 2 years earlier. This is the story of how American industrial might transformed invention into overwhelming tactical advantage. Not through brilliant innovation, the British had done the innovating, not through superior technology. German and British radar systems were often more sophisticated, but through sheer manufacturing capacity applied systematically until radar appeared everywhere simultaneously, on fighters, on bombers, on ships, mounted on trucks defending beachheads, protecting cities, hunting submarines. It's proof that wars aren't won by the best technology. They're won by whoever can produce adequate technology in quantities that make enemy adaptation impossible. The path to that moment over Saipan had begun nearly 4 years earlier, 3,000 miles away, in a hotel room in Washington, D.C. that would witness one of the war's most consequential meetings. September 19, 1940. The United States wasn't at war yet. Pearl Harbor was 15 months away, but Britain was dying. The Luftwaffe had been bombing London for 10 days straight. The Battle of Britain raged over Kent and Sussex. Invasion barges massed in French ports. Winston Churchill was making desperate calculations about how long Britain could survive alone. And on that September afternoon, in Alfred Loomis's apartment at the Wardman Park Hotel, a British physicist named Edward George Bowen opened a black japanned metal trunk that had traveled 3,000 miles from Birmingham. 12 men crowded the room. American scientists, military officers, representatives from the National Defense Research Committee. They'd been told the British were bringing secret technology. They expected blueprints, maybe some radar components. Bowen reached into the trunk and withdrew a copper block roughly the size of a grapefruit. 8 cavities ringed its circumference. It weighed perhaps 2 pounds. A wire led from its center. "Gentlemen," Bowen said, placing it on the polished mahogany table, "this is magnetron E1189, serial number 12, the cavity magnetron." Alfred Loomis, millionaire physicist, cousin to Secretary of War Henry Stimson, picked it up, turned it over in his hands. The device was warm from Bowen's jacket pocket. "What's the power output?" asked a naval officer whose name isn't recorded in the minutes. 10 kilowatts, continuous pulses, at 9.1 centimeter wavelength. The room went silent. America's best microwave tube, developed by Bell Laboratories after years of research, produced 40 watts. 40 watts at wavelengths measured in meters, requiring antennas the size of furniture to transmit and receive the signals. This British device, small enough to fit in a briefcase, claimed to produce 10,000 watts, 250 times more powerful, at wavelengths measured in centimeters, requiring antennas no larger than a dinner plate. Loomis looked at Bowen. "You're certain of this figure?" "We've measured it repeatedly," Bowen said. "In some tests, we've achieved 100 kilowatts peak output. The device is limited more by our power supplies than by the magnetron itself." Within the hour, Bell Laboratories engineers were examining the magnetron at their facility in Murray Hill, New Jersey. By the next morning, they'd confirmed it worked exactly as described. Within a week, they'd built their first American copy. And within 2 weeks, Vannevar Bush, chairman of the National Defense Research Committee, architect of America's scientific mobilization, had made the decision that would reshape the war's trajectory. The United States would build a laboratory dedicated solely to radar development. Not in Washington, where bureaucracy and security concerns would slow progress. Not at a government facility where civilian contractors couldn't access classified research. In Cambridge, Massachusetts, on the MIT campus, where academic researchers and industrial engineers could work side by side with minimal oversight and maximum freedom to innovate. The Radiation Laboratory, deliberately misnamed to suggest nuclear physics research rather than radar work, opened its doors on November 11, 1940. Lee Dubridge, a 39-year-old physicist from the University of Rochester, arrived to direct it. He'd been given an impossible assignment: turn a British prototype into production radar systems that American factories could manufacture by the thousands. 80 people worked there in December 1940, crammed into rooms in Building 4 on the MIT campus. By December 1941, 400 employees. By December 1942, 1,700. By war's end, 3,897 employees working in over 400,000 square feet of laboratory and office space, developing over 150 different radar systems. The Rad Lab's first assignment was straightforward: understand how the cavity magnetron worked and why it was so much more powerful than existing tubes. The second assignment was harder: design radar systems that could be manufactured by companies with no electronics experience. Britain had proven radar worked. Their chain home system had detected incoming Luftwaffe raids during the Battle of Britain. Their H-2S terrain mapping radar guided bombers through clouds over Hamburg and Berlin. Their ASV Mark III air-to-surface radar detected submarines running on the surface at night in the Atlantic. But British factories couldn't produce enough radar sets to matter strategically. Their production lines were bomb-damaged, their workforce exhausted, their materials allocated to Spitfires and Lancaster bombers and destroyer escorts. When the Tizard Mission arrived in Washington, Britain was producing approximately 50 radar sets per month across all types combined. America approached the problem from a completely different angle. Western Electric sent engineers to Cambridge within days of the Rad Lab opening. So did General Electric, RCA, Raytheon, Chrysler, and Westinghouse. They didn't wait for finished designs. They watched prototypes being hand-assembled by physicists and asked the questions that physicists never ask. Can this component be stamped instead of machined? Can this tolerance be loosened to 0.005 inches instead of 0.001 inches? Can this vacuum tube be replaced with a standard type already being produced by the millions for commercial radios? Can semi-trained workers assemble this, or does it require a PhD in electrical engineering? Every answer changed the design. Every change made mass production more feasible. By early 1942, two major programs were underway, both designed from day one for manufacturing at scale. Project Cadillac focused on automatic gun-laying radar that could track aircraft and compute firing solutions without human intervention. The designation SCR-584. The goal? Deploy it everywhere anti-aircraft guns defended critical facilities. Project Black Widow focused on airborne interception radar small enough and light enough to fit inside a night fighter. The designation SCR-720. The goal? Put it on every fighter operating in darkness. Both systems used the cavity magnetron. Both would revolutionize their respective missions. Neither would matter strategically unless American factories could build them faster than combat consumed them. The 6th Night Fighter Squadron received their first P-61 Black Widows on May 1, 1944 at Guadalcanal in the Solomon Islands. Pilots who'd been flying Douglas P-70s, converted A-20 bombers with British AI Mark IV radar crudely installed in the nose, stared at the new aircraft in disbelief. The P-61 was massive. Wingspan, 66 feet, wider than a B-25 Mitchell bomber. Length, 49 feet. Height, 14 feet 8 inches. Empty weight, 23,000 pounds. Maximum gross weight, 32,000 pounds, fully loaded with fuel, ammunition, and crew. Twin Pratt & Whitney R2800 double Wasp radial engines, each producing 2,000 horsepower at war emergency power settings. Four-bladed propellers, 13 feet in diameter. Maximum speed, 366 miles per hour at 20,000 feet. Service ceiling, 33,000 feet. Combat radius, 1,000 miles. Armament, 4 20mm Hispano M2 cannons mounted in the belly, each loaded with 200 rounds. 4 50-caliber Browning M2 machine guns in a remote-controlled dorsal turret, later removed from many aircraft because the buffeting it caused interfered with radar accuracy. And in the nose, behind a fiberglass radome painted flat black to minimize reflection, the SCR-720C radar with its rotating dish antenna and complete operator station. Captain Dale Haberman flew his first combat patrol on June 25, 1944. Nothing. The skies over Saipan were empty. Japanese aircraft had learned to avoid American-controlled airspace during daytime. Allied fighters had achieved near-total air superiority. But intelligence indicated that Japanese bombers still flew nuisance raids at night. Single aircraft or small formations targeting supply dumps, fuel depots, and ammunition stockpiles. The P-61's mission was simple: find them in darkness and destroy them before they reached their targets. 5 nights later, June 30, 1944, at 2:47 in the morning, Haberman got his vector. The engagement demonstrated what American mass production had achieved. The radar detected the target at 15 miles, 3 times beyond visual range in darkness. It tracked the target through evasive maneuvers. It guided Haberman into firing position without external communication or ground-based direction. The Japanese crew never knew death was tracking them until 20mm shells ripped through their fuselage. The 418th Night Fighter Squadron arrived in the Pacific in July 1944, equipped with 12 P-61s. The 421st followed in August with 14 aircraft. By September 1944, 8 P-61 squadrons were operating across the Pacific Theater, from New Guinea to the Philippines, from China to the Mariana Islands. Japanese night raids decreased immediately. Not because the Japanese stopped trying, because the P-61s were killing them faster than replacement crews could be trained. On August 5, 1944, the 419th Night Fighter Squadron scored its first kill over Tacloban. The 547th followed on August 20th with 2 victories in a single night. By October, Japanese pilots were reporting encounters with American fighters that could track them through clouds, through darkness, through weather conditions that made visual interception impossible. Some suspected radar. Most didn't believe it was possible to miniaturize radar enough to fit in a fighter. A few thought American pilots had developed superhuman night vision through special diets or training programs. The truth was simpler. American industrial capacity had produced 706 P-61 Black Widows by war's end, each equipped with an SCR-720 radar system, each crewed by pilots and radar operators who'd trained for months at purpose-built schools in Florida and California. Production and training infrastructure at scale. But air combat was only half the story. The SCR-584 was solving a different problem, one that had plagued anti-aircraft gunners since 1914. Before radar, shooting down aircraft required visual spotting, manual tracking, and calculated lead, mathematics performed by humans while the target moved at 300 miles per hour and the shell took 40 seconds to reach altitude. Hit rates against fast-moving targets? Approximately 2%. The SCR-584 changed the mathematics. The system's requirements were brutal. Detect aircraft at 40 miles range, automatically track targets at 18 miles, feed continuous targeting data to 90mm anti-aircraft guns with sufficient precision to hit bombers traveling 300 miles an hour at altitudes up to 30,000 feet. Do all of this while mounted on trailers that could be towed behind trucks, set up in field conditions within hours, and operated by soldiers who'd received 6 weeks of training. The calculations were unforgiving. A bomber at 20,000 feet traveling 300 miles an hour covers 440 feet per second. A 90mm shell takes approximately 40 seconds to reach that altitude. During those 40 seconds, the bomber travels 17,600 feet, more than 3 miles. The gun must fire not at where the target is, but at where it will be when the shell arrives. The SCR-584 made the calculation automatically, continuously, and with precision no human could match. The system consisted of multiple components spread across several trailers. The radar unit itself, a 6-foot parabolic dish antenna mounted on a rotating platform capable of traversing 360 degrees in azimuth and from -5 to +90 degrees in elevation. 300 vacuum tubes, miles of wiring, servo motors to rotate the dish and track targets automatically, a transmitter generating pulses of microwave energy at 3,000 megahertz, a receiver sensitive enough to detect reflections from a single bomber at 40 miles. Connected to the radar, the M9 director, an analog computer that received continuous position data and computed firing solutions in real time. The M9 accounted for target altitude, speed, bearing, rate of climb or descent, wind velocity at multiple altitudes, air temperature, barometric pressure, and the ballistic characteristics of the specific ammunition being fired. It performed these calculations 30 times per second, updating the firing solution continuously as the target maneuvered. Chrysler's Dodge division took the contract to manufacture the SCR-584 in June 1942. They had been building automobiles. Now they were building electronic systems more complex than anything in a B-29 Superfortress. The learning curve was vertical. Engineers from Bell Laboratories embedded themselves at the Dodge plant in Detroit. They worked on the assembly line, watched where workers struggled, identified which steps took too long or required too much precision. Every observation led to design changes. Vacuum tube sockets were redesigned so tubes could only be inserted one way, eliminating installation errors. Wiring harnesses were pre-assembled and color-coded. Mechanical assemblies were machined to looser tolerances that still maintained function. The M9 Director's gear trains were simplified. By August 1943, 14 months after the contract was signed, Chrysler had delivered 610 complete SCR-584 systems. The Signal Corps initially ordered 1,470 units total. They believed Allied air superiority would make more unnecessary. They were wrong. Final production, 2,098 systems for the Army, plus an additional 628 sets for the Marines and Coast Defense. Monthly production rate peaked at 200 units in early 1945. February 24, 1944, Anzio Beachhead, Italy. The Allied invasion force had landed on January 22, pushing inland against weakening German resistance, but the Luftwaffe still controlled the night skies. German bombers attacked the beachhead nightly, Ju-88s and Do-217s dropping bombs on supply dumps, fuel depots, ammunition storage, and the packed transport ships offshore. The defenders had SCR-268 radars, older systems that worked adequately but could be jammed with chaff and deceived with basic electronic countermeasures. Hit rates against fast-moving targets, approximately 15%. On February 24th, 2 SCR-584 units arrived after dark, towed by Diamond T trucks through shell-cratered roads. The crews, members of the 90th Anti-Aircraft Artillery Battalion, had trained on the systems for 6 weeks at Fort Bliss, Texas. They'd never seen combat. They dug the trailers in that night, positioning them 2 miles apart to provide overlapping coverage. Radar trailer, generator trailer, M9 Director trailer, all connected by thick cables and communication lines. Camouflage nets went up by dawn. Power generators were tested. The 6-foot dish antennas rotated smoothly on their mounts. By sunset on February 25th, both systems were operational. At 22:17 hours, 10:17 p.m., the first contacts appeared on the scopes. Multiple targets, bearing 270, range 38 miles, the radar operator reported to the gun battery commander. His voice was steady despite his hands shaking. Count 12 aircraft in formation. The SCR-584 locked onto the lead aircraft. At 18 miles range, automatic tracking engaged. Servo motors whined as the dish rotated to follow the target. Data flowed to the M9 Director, range decreasing at 240 miles per hour, altitude 18,000 feet, bearing 268 degrees. The M9 computed the firing solution. The 90mm guns, 4 of them positioned in a semicircle around the radar, traversed automatically. No human aimed them. The Director sent electrical signals directly to the gun mounts, which rotated to the computed azimuth and elevated to the computed angle. At 14 miles range, the guns opened fire. Shells climbed toward the calculated intercept point. The radar continued tracking. The M9 continued updating the solution 30 times per second. More shells fired. The barrage created a box in the sky where the bomber would be in 40 seconds. The first bomber exploded at 22:19 hours, 2 minutes from first detection to kill. The second fell 30 seconds later. By 22:25, 8 minutes after the raid began, 7 German bombers had been destroyed. The remaining 5 scattered, abandoning the attack run, fleeing back toward their bases in northern Italy. The 90th AAA Battalion's guns had fired 127 rounds, 7 kills, a hit rate of 5.5% per shell, nearly 3 times better than the best manual gun-laying crews achieved. But the real metric was different. 12 bombers attacked, 7 destroyed before reaching their targets, 5 forced to abort. The raid failed. The supplies at Anzio remained intact. No ships were hit. Luftwaffe attacks on Anzio continued sporadically for the next week, probing different approach vectors, testing whether the radar coverage had gaps. On March 2, a single JE-88 approached from the northwest at wave-top altitude, trying to slip under the radar horizon. The SCR-584 detected it at 43 miles, the aircraft's metal skin reflecting microwave energy even at low altitude. Automatic tracking engaged at 22 miles. The guns destroyed it at 14 miles, 6 minutes from first detection to confirmed kill. After March 8, 1944, German bombers stopped attacking Anzio at night, not because they'd been defeated elsewhere, not because they'd been reassigned to other missions, because the mathematical reality was undeniable. SCR-584 equipped defenses were destroying German aircraft faster than replacement crews could be trained. 10 additional SCR-584 systems arrived at Anzio by the end of March. By June 1944, the Normandy invasion, Allied forces had deployed over 400 SCR-584 systems across England, Italy, and North Africa. The real test came 3 months later against a target that didn't think, didn't evade, and flew in perfectly straight lines at constant speed and altitude. June 13, 1944, 7 days after D-Day, Germany launched the first V-1 flying bomb against London. The Fieseler Phi-103, officially designated FZG-76 by the Luftwaffe, was a cruise missile before the term existed. Length 25 feet. Wingspan 17.5 feet, launch weight 4,750 pounds, including a 1,870-pound Amatol warhead. Powered by an Argus AS-109-014 pulse jet engine, producing 660 pounds of thrust, the V-1 flew at speeds between 350 and 400 miles per hour at altitudes between 2,000 and 3,000 feet. It was fast enough that most fighters couldn't catch it before it crossed the English Channel. It was small enough that visual spotting gave defending forces less than 2 minutes warning. It flew in a straight line from launch to impact, requiring no mid-course guidance, and Germany could produce approximately 100 of them per day. British defense planners faced a terrible equation. Intelligence indicated Germany had deployed hundreds of launch sites along the French coast. If each site launched just 2 V-1s per day, London would face 400 attacks daily. Even with a 20% interception rate, 300 warheads would hit the city every single day. The mathematics demanded better than 20% interception. The British deployed SCR-584 units in a belt along the coast, the Diver Belt, named after the operation to counter the V-1 threat. Gun batteries equipped with SCR-584 radars and M9 directors positioned in overlapping coverage zones from Dover to Portsmouth. On July 16, 1944, 1 month after the V-1 offensive began, a flying bomb crossed into British airspace at 400 miles per hour and 2,800 feet altitude. The SCR-584 detected it at 28 miles. The target moved too fast for visual tracking, too straight for evasive prediction, but the radar didn't care about speed or trajectory. It simply measured where the target was, computed where it would be, and directed the guns. Automatic tracking engaged at 16 miles. The M9 calculated the intercept solution. The 3.7-inch anti-aircraft guns, British weapons fed American targeting data, fired a predicted barrage. The V-1 disintegrated at 8 miles from the guns, destroyed by shells that had been fired before the target reached the calculated intercept point, detonating in a cloud of fragments the V-1 flew directly into at 400 miles per hour. Time from detection to destruction, 4 minutes, 12 seconds. By August 1944, British gun crews using SCR-584 systems were achieving 74% kill rates against V-1 flying bombs. Not 74% of shells fired achieved hits, 74% of detected V-1s were destroyed before reaching their targets. The mathematics became brutal for Germany. They could produce 100 V-1s per day. Britain could destroy 74 of them with automated radar-directed guns positioned in a defensive belt that cost a fraction of what the V-1 production and launch infrastructure required. The remaining 26 V-1s that penetrated the diver belt each day still reached London, still killed civilians. The terror weapon aspect worked, but 26 warheads per day killed an average of 52 people, not the thousands per day that conventional bombing raids had achieved in 1940-41. Germany built approximately 10,000 V-1 flying bombs total before the launch sites were overrun by Allied ground forces in August and September 1944. Britain deployed over 2,000 SCR-584 systems in England alone by war's end. When you can build defensive systems faster than the enemy can build offensive weapons, attrition mathematics favored the defender even when individual interceptions aren't perfect. The SCR-584's design reflected a fundamentally American approach to engineering problems that European militaries didn't fully grasp until it was too late. The MIT Radiation Laboratory had examined British radar systems in late 1940 and asked a question British engineers hadn't prioritized. What would it take to build 10,000 of these? The answer required complete redesign for mass production. Every component was standardized to existing commercial specifications wherever possible. Vacuum tubes weren't custom designed, they were off-the-shelf types already being produced by the millions for civilian radio receivers. The 6AC7 pentode tube used in the SCR-584 receiver was identical to the tube and table radios made by Philco and RCA. When a tube failed in combat, replacement didn't require waiting for specialized military parts. Any supply depot with radio components had compatible tubes. Resistors, capacitors, and transformers came from existing supplier catalogs. Nothing was custom built unless absolutely necessary for performance. Even the M9 director, the most complex component, used mechanical computing elements that Chrysler engineers already understood from automobile transmission design: differential gears, planetary gear sets, cam-operated linkages. These were technologies Chrysler had been manufacturing for decades. The M9 simply used them to solve ballistic equations instead of converting engine torque into wheel rotation. The antenna mounting system was pure American automotive engineering. Ball bearings from suppliers who manufactured them for truck wheel assemblies. Servo motors adapted from aircraft autopilot systems. Gear reduction drives similar to those used in tank turret traverse mechanisms. Bell Laboratories had designed it. Western Electric had engineered it for production. But the true innovation wasn't the radar itself, it was designing the radar so that companies with no electronics experience could build it after 6 weeks of training. By August 31, 1943, 14 months after the manufacturing contract was signed, Chrysler had delivered 610 complete systems. Workers who'd been stamping car fenders in 1941 were now assembling microwave radar systems with 300 vacuum tubes and miles of color-coded wiring. Compare this to German radar production. The Würzburg system, Germany's primary gun-laying radar, entered service in 1940. By 1945, approximately 4,000 units had been produced across all variants: the basic Würzburg with a 3-meter dish, the Würzburg Ries, giant Würzburg with a 7.5-meter dish, and various specialized versions for different applications. 4,000 units over 5 years, an average of 67 units per month. The Würzburg Ries was technically impressive. Its larger antenna provided better angular resolution than the SCR-584. Its maximum range, approximately 40 miles for bomber-sized targets, matched American performance. In some ways, it was superior. The Ries could track targets down to 500 meters altitude, while the SCR-584 lost accuracy below 1,000 meters due to ground clutter. But Germany couldn't produce enough Würzburgs to deploy them everywhere they were needed. Each system required precision manufacturing. The dish antenna alone required specialized tooling and skilled metalworkers. The electronics used custom-designed tubes that had no civilian equivalents. More critically, each Würzburg required a trained crew of specialists: operators who understood the system's quirks and limitations, maintenance technicians who could diagnose and repair sophisticated electronics, calibration specialists who kept the system operating at peak accuracy. America accepted looser tolerances, broader training, and modular replacement instead of field repair. An SCR-584 didn't need to be perfect, it needed to be good enough, deployed everywhere, maintained by semi-skilled crews who swapped out entire modules when problems arose instead of diagnosing individual component failures. While the SCR-584 was defending beachheads and shooting down V-1s, the P-61 was demonstrating adaptability that mass production enabled. Late 1944, European theater. The 422nd Night Fighter Squadron operated P-61 Black Widows from Belgian airfields starting in October. Their primary mission wasn't intercepting Luftwaffe bombers. The German Air Force had been defeated in daylight combat and rarely flew at night by late 1944. Instead, the 422nd hunted trains. Locomotives showed up beautifully on radar. The SCR-720 could detect a moving train at 12 miles, distinguish it from ground clutter, track it through forests and hills, and guide the pilot to visual range without the target ever knowing it was being followed. Pilot Hermann Ernst and radar operator Edward Kospel flew together for 8 months starting in November 1944. They became aces, 6 confirmed aerial kills including 1 V-1 flying bomb destroyed in mid-flight, but their train-busting statistics were more impressive. 43 locomotives destroyed, uncounted rail cars demolished, and infrastructure damage that forced Germany to move supplies by daylight when Allied fighter bombers could destroy them even more easily. On the night of December 21, 1944, during the Battle of the Bulge, Ernst and Kospel flew 3 missions in 18 hours. They destroyed 5 locomotives, damaged 2 rail bridges, and strafed a supply convoy moving through a forest road. The radar allowed them to operate in weather that grounded every other aircraft in the theater. Cloud ceiling at 800 feet, visibility less than 1 mile, freezing rain. German ground forces during the Bulge offensive faced a terrible problem. They couldn't resupply at night because American radar-equipped fighters could see in darkness, and they couldn't resupply during daytime because American fighters controlled the skies. The Ardennes offensive collapsed partly because logistics became impossible. This wasn't brilliant strategy, it was mass production creating opportunities that hadn't existed before. The 422nd had enough P-61s that they could afford to assign them to secondary missions like train interdiction. If production had been limited to 50 aircraft total, enough for primary air defense missions only, those locomotives would have kept running. Quantity created flexibility. Flexibility created options commanders hadn't previously considered. The numbers. Production statistics. SCR-584 units Army, 2,098 complete systems. SCR-584 units Marines and Coast Defense, 628 additional sets. Total SCR-584 production, 2,726 systems. SCR-720 airborne radar units, approximately 2,000, all variants. P-61 Black Widow aircraft, 706 total, including 36 F-15A photo reconnaissance variants. Peak monthly production, SCR-584, 200 units, January to March 1945. Cavity magnetron E1189 power output, 10 kilowatts continuous at 9.1 centimeter wavelength. Power improvement versus existing U.S. technology, 250x from 40 watts to 10,000 watts. SCR-720 detection range, 40 miles, bomber-sized targets. SCR-584 automatic tracking range, 18 miles maximum. SCR-584 accuracy, 25 yards range error, 0.06 degrees bearing error. SCR-720 detection range, 5 miles minimum, expanded sweep, 20 miles typical. SCR-720 system weight, 412 pounds, complete installation. P-61 Black Widow maximum weight, 32,000 pounds, fully loaded. P-61 maximum speed, 366 miles per hour at 20,000 feet. P-61 combat radius, 1,000 miles. Comparative production data. German Wurzburg radar production, all variants 1940 to 1945, approximately 4,000 units.
Average German radar production rate, 67 units per month. Average American SCR-584 production rate, 1943 to 1945, 113 units per month. British radar production, peak monthly, all types, approximately 50 units.
August 15, 1945. The war ended at noon Tokyo time when Emperor Hirohito's surrender broadcast aired. But in the skies over Japan, one final engagement was still unfolding. Lieutenant Lee Kendall of the 548th Night Fighter Squadron was flying his P-61 Lady in the Dark on a routine patrol when his radar operator detected a contact at 14 miles. A Japanese fighter, later identified as a Nakajima K-44 Tojo, apparently hadn't received word of the surrender or had chosen to ignore it. Kendall maneuvered to intercept. The Japanese pilot spotted the P-61 and dove for the deck, trying to escape at wave-top altitude where ground clutter would mask his radar return. It was a tactic that worked against earlier radar systems. The SCR-720C didn't lose contact. Kendall followed through the dive, tracking the enemy fighter through every turn, every altitude change. The Japanese pilot was skilled. He'd survived this long by being skilled, but he was fighting technology he didn't understand with tactics that didn't work. After 3 minutes of maneuvering at maximum speed and minimum altitude, the Japanese fighter struck the water during a hard turn. The impact at 350 miles per hour was catastrophic. The aircraft disintegrated. Kendall pulled up, circled once, saw only debris on the water. The last aerial victory of World War II went to an American P-61 Black Widow equipped with radar that had been invented by the British, engineered by Americans, and mass-produced by a company that made telephones. Not glorious or particularly meaningful, the war was already over, that pilot's death changed nothing, but fitting as a demonstration of what had actually won the war. Not the radar itself. Germany had radar, Britain had radar, Japan was developing radar by 1945. The technology wasn't secret, the principles weren't particularly complex once the cavity magnetron solved the power and wavelength problems. What won was production capacity applied systematically until the technology appeared everywhere, on fighters, on bombers, on ships, on mobile anti-aircraft batteries, defending beachheads, protecting cities, hunting submarines in the Atlantic. The MIT Radiation Laboratory closed in December 1945, its mission complete. The 3,897 employees who'd developed over 150 radar systems dispersed to universities, to industry, to government laboratories. But the principles they'd established, rapid prototyping, design for mass production, government, industry, academic cooperation, became the foundation for every major defense development that followed. When the Soviet Union detonated an atomic bomb in August 1949, America responded with the SAGE air defense system, radar stations networked by computers, directing interceptors toward incoming bombers, deployed across the continent in overlapping coverage that made destroying individual sites strategically meaningless. The philosophy was identical: build enough systems to make the enemy's problem mathematically impossible. The cavity magnetron itself evolved far beyond military applications. Microwave communications towers, satellite ground stations, radar altimeters for commercial aviation, microwave ovens in suburban kitchens, using the same basic technology that had tracked V-1 flying bombs over London. But the real legacy wasn't technical, it was philosophical and industrial. Britain invented the cavity magnetron in February 1940. America turned it into a weapon system and built it in quantities that overwhelmed enemy countermeasures through sheer numerical superiority. Not because American scientists were smarter, they weren't. British scientists had done the fundamental discovery work. Not because American engineers were more creative, many weren't. German engineering was often more sophisticated, but because American factories could convert automotive production lines to electronics manufacturing in months, train workers in weeks instead of years, accept looser tolerances that still delivered adequate performance, and produce complex systems at rates that made individual unit performance almost secondary to total deployment numbers.
The Japanese pilot who died on August 15, 1945, fled from a P-61 equipped with radar because America had built 706 Black Widows. Germany's V-1 offensive failed because America had built 2,726 SCR-584 systems. The Battle of the Atlantic turned in mid-1943, partly because America had produced enough ASV radar systems to equip every anti-submarine aircraft that mattered. Those production numbers represented a fundamental truth about modern warfare that Germany and Japan never fully grasped. Breakthrough innovation is only half the battle. The ability to produce adequate technology at overwhelming scale is what actually wins wars.
This principle, unsexy, unglamorous, purely industrial, defined American military power for the next 80 years. It's why military planners obsess over production capacity and supply chains as much as weapon performance. It's why the F-35 fighter program, whatever its technical merits, succeeded partly because it created a production infrastructure that can build aircraft faster than potential adversaries can develop countermeasures. The secret weapon Britain gave America wasn't really the cavity magnetron. The magnetron was just copper and cavities and physics that any competent engineer could eventually replicate. The secret weapon was the American industrial base's ability to take that copper device and turn it into 100,000 magnetrons, 2,000 SCR-720 radars, 2,726 SCR-584 systems, and over 150 different radar types, all within 5 years, all while simultaneously building 300,000 aircraft, 100,000 tanks, and the atomic bomb. That's the weapon that won World War II. Not genius, not innovation. Production capacity, applied systematically until numbers overwhelmed capability and quantity became its own quality. The mathematics were always brutal. They still are.